Have you ever wondered why your sensor readings might not always be perfectly precise, even from a well-designed system? Sensor linearity correction methods are essential techniques used to improve the accuracy of sensor measurements by compensating for their nonlinear behavior. They ensure the output truly reflects the physical quantity being measured, providing a more reliable and predictable response. The primary methods typically involve mathematical models like polynomial fitting, data-driven approaches using lookup tables, and analog circuit compensation. Many physical sensors inherently produce an output that is not perfectly proportional to the input over their entire operating range. This nonlinearity arises from the fundamental physics of the sensing element, material properties, temperature dependencies, or manufacturing variations. A linear sensor would ideally have a straight-line relationship between its input and its output. However, in reality, this transfer function often curves or deviates. Correcting this nonlinearity is crucial because accurate measurements are the foundation for reliable control systems, precise data acquisition, and robust decision-making in embedded applications. Without it, a temperature sensor might report 40 degrees Celsius when it is actually 45, leading to incorrect system responses. Polynomial fitting is a digital method that models the sensor's nonlinear behavior with a mathematical polynomial equation. Engineers collect calibration data points by applying known inputs and recording the corresponding sensor outputs. Then, they use regression analysis to determine the coefficients of a polynomial that best fits these data points. For example, a second-order polynomial might be used for a slightly curved response, while a higher-order polynomial can capture more complex nonlinearities. The microcontroller then applies this polynomial equation to raw sensor readings to produce a corrected, linear output. Another common digital approach involves storing a lookup table of correction values. During calibration, the sensor's output for various known inputs is measured and stored. When the sensor is in operation, its raw output is used to find the closest entry in the lookup table. The corresponding corrected value, or an interpolated value between two entries, is then provided as the linear output. This method is particularly effective for highly irregular nonlinearities, or when computational resources for complex polynomial calculations are limited. Sometimes, linearity correction can be implemented directly in the analog domain before the signal is digitized. This involves designing specific analog circuits, often using operational amplifiers, resistors, and capacitors to counteract the sensor's nonlinear response. For instance, a circuit might be designed to have a complementary nonlinear characteristic that, when combined with the sensor's output, results in an overall linear system. This approach can be beneficial for high-speed applications or when minimizing digital processing overhead is critical. To implement these corrections, you first characterize your sensor by subjecting it to a range of known inputs and recording its corresponding outputs. This creates your calibration curve. For polynomial correction, you then apply a curve-fitting algorithm to derive the coefficients. For lookup tables, you simply populate the table with the measured input-output pairs or interpolated values. For analog compensation, careful circuit design and component selection are paramount to achieve the desired response. Selecting the appropriate method often depends on the required precision, available computational power, and acceptable latency. For example, a higher-order polynomial offers greater accuracy but demands more processing power, while a lookup table might consume more memory. Analog compensation, while fast, can be less flexible to changes or environmental drift compared to software-based methods. These trade-offs, often balancing cost versus performance, are key considerations in embedded system design. By applying these carefully chosen linearity correction techniques, engineers can transform inherently imperfect sensor signals into highly accurate and reliable data. This not only enhances the performance and robustness of embedded systems, but also ensures that critical decisions are based on the truest representation of the physical world. It is a fundamental step in achieving trustworthy measurements and unlocking the full potential of sensor technology.